All right, let's work through a few power series examples. Here's one where you're given a power series for a function, and let me highlight this is the power series, and that is the function. And the question is to determine a power series for this new function. So I'm trying to find a power series for this new function. And this new function happens to be its first derivative. So let's go ahead and do that one. I'll take the first derivative, f prime of x. We'll do each piece at a time. So this one, as a function, you might do the quotient rule if you want, which is fine. You are welcome to also think of it as 1 plus x to the negative 1, and its derivative is negative 1 times 1 plus x to the negative 2. That's using the power rule, which of course you can simplify if you'd like as negative 1 over 1 plus x squared. Okay. But you can't just take the derivative of one side of the equal sign. You have to also take the derivative of the other side. So now I'm going to look at the actual power series, and I'll have the sum from n equals 0 to infinity of, I can do the chain rule, because this really is a power rule with a chain rule. I can bring the n down, leave the inside the same, subtract 1 from the power. Don't forget to multiply by the derivative of the inside, which in this case was negative 1. And then we can simplify from there. So this will become the negative 1 plus x squared equals, I'm going to rewrite that as the sum from n equals 0 to infinity of negative n times negative x to the n minus 1. But that negative x to the n minus 1 could be written as a negative 1 to the n minus 1, and then an x to the n minus 1. And then there is the technicality behind all of this is that the power series does not have negative exponents. A series definitely could, but there's the technicality that a power series does not. And also another thing to notice, if I started at n equals 0, that would just give me 0. So I don't need to start at n equals 0. I can just choose to start at n equals 1, and then I can re-index. So negative 1 over 1 plus x squared. If I were to re-index, there was a re-indexing, or what you might call a shift of the index. So from here to here, I will shift the index along the way, if I can write that. There we go. Okay, and to do that, if your index is going to go down by 1, then everything else needs to go up by 1 to keep that balanced. So this will become the sum from n equals 0 to infinity of negative n plus 1, negative 1 to the n, and then x to the n. Each one of these guys, let me highlight that a little clearer, sorry. Each one of those guys went up by 1, everything else stayed the same. Ta-da! Okay, so that is the power series representation for that function. You can see that it didn't ask for an interval of convergence. That would be another step that you could do. This was geometric, so the interval of convergence started off with x being in between 1 and negative 1. But let's move on. Let's do another example of integrating and differentiating power series, okay? So the next example I have is starting off with geometric again. Let me make it so you can see it. Here we go. Starting off with geometric again, this one gets a little trickier pretty quick. So that's why I wanted to talk about this one. The question says to either use differentiation or integration to find a power series for a new function. And that or really is just saying, like, you decide what makes the most sense. There's more than one way to go about this problem. And so we'll go ahead and do that. We know our power series for the geometric series is 1 on 1 minus x is the sum from n equals 0 to infinity of x to the n. That was given. I just wrote it in a different order. The order of that equal sign does not matter. It was just a habit of mine to write it in that order. It doesn't matter. And I want to try to see if I can find a way to get this to look like the function in question. Okay, so we now write out my function in question. So f of x is equal to ln of 2 minus x is my function. I want to try to take this function and somehow or another get it to look like something that I know, which is the geometric power series. That's something that I know. So there's multiple ways to do this. Like we said, there's definitely more than one way to do this. I'm going to do a little bit of yoga for the brain here and realize that if I wanted to take the derivative of this function, I could, and if I took the derivative of that function, it would look kind of close to the geometric power series. So this is all about manipulating what you have to get something that would be helpful. And like I said, there's more than one way to do this problem, but we're gonna just show you one way. So let's try that here. I'm gonna take the derivative of my function, which is 1 over 2 minus x times -1 because the chain rule. And then I'm going to simplify that even a little bit farther. That's a -1 over. Now that 2 minus x on the bottom does not quite match. Ooh, sorry about that. Does not quite match the bottom of my geometric series. So I'm going to factor out that 2 and see what happens there. If I factor out the 2, then I'd be left over with the 1 minus x over 2, which I could rewrite as -1/2 times 1 over 1 minus x over 2. And the reason I do that, and I'll highlight it so you guys can see, I just think it's a little bit more visual to actually see. Now, instead of an x, I have an x over 2. So I do have some kind of comparison now between the two. So that's pretty good. Let's see what I can do to keep going, though. So that means that this could equal -1/2 times the sum from n equals 0 to infinity of x to the n. But instead of an x, I have an x over 2. So that really should be an x over 2. You're trying to compare what I have versus what I know. What I have is the x over 2. What I know is if it were just an x. The -1/2 was just a constant multiple, so I just left it there and I'll deal with it later. Okay, all right, and then I'm gonna choose to simplify that. There's definitely multiple ways I could simplify that, but I'll go ahead and do that right now. It's the sum from n equals 0 to infinity of -1/2 times x to the n over 2 to the n, and then you can see that those 2 to the n's can could combine, and I'll end up with a -1 over 2 to the n plus 1. Cool. Okay, so I simplified that. I got to make sure I know what I even did. There was more than one way to do this, so we have to go back and make sure what it is that I did. In this problem, I chose to take my function and take a derivative. And then I did that, I did its derivative, and then following through those equal signs, I now have a power series representation. This is the power series representation for my function's derivative. If I go back and look, though, the question is asking me for a power series of my original function, f of x. I want a power series of my function, f of x. So I gotta be pretty careful with that. Right now I have a power series function for f prime. What I need is a power series function for f of x. So how do I go back to f of x? If I have f prime, but I need f, the only way to do that is to find an antiderivative. So we'll go ahead and find an antiderivative, or take the antiderivative or the integral of both sides of that equal sign. Okay, and that's what we'll do. So I'm going to end up with the sum from n equals 0 to infinity. The -1 over 2 to the n plus 1 is just a constant multiple, so it stays. So we're taking the antiderivative of the x's, though. So then that'll become an x to the n plus 1 over n plus 1. Cool, but remember, when you do an antiderivative, there is that plus c, so I have to be careful with that. And I don't want to keep scrolling back up, so I'm going to just write down so I don't forget. I need to remind myself what my f of x was. My f of x was ln of 2 minus x, just kind of keeping that true equal sign there so I know I had a power series for f prime. Now I have a power series for f, but I have to kind of think about that plus c for a second. So there's some multiple strategies to go about this. X equals 0 is a very easy number. So I always recommend that you just plug in x equals 0, or really whatever the center of that power series is. And in this case, the center was 0. We were working with the geometric series. So if I plugged in 0, then all of those x's are going to go to 0. If I plugged in x equals 0, then all of these x's are going to go to 0. And if I plugged in x equals 0 on the left-hand side of that equal sign, I'm going to get ln of 2. On the right-hand side of that equal sign, I'm going to get c, which means that plus c actually matters here. There's some other ones where that plus c ended up being 0, and so it didn't matter. But here it did matter. I had a kind of trick here. So now I have ln of 2 minus x equals the sum from n equals 0 to infinity of -1 over 2 to the n plus 1 x to the n plus 1 over n plus 1 plus my c. So all I did here again is I just copied this down right as it is, but I had solved for c, so now I can write it out as the c. And then there is just another way that it can be written. This is not necessary, but it tends to look a little bit prettier if you put those loose constants before the sigma notation, because that wasn't part of the sigma notation. So I'll put that before, plus the sum from n equals 0 to infinity of -1 over 2 to the n plus 1 times x to the n plus 1 over n plus 1. And you're welcome to take that negative on the outside of that sigma notation because it was a constant multiple. So now I have a power series representation for that function. Now this is a power series right here, but with a added of a number, it still counts as a power series because that's just a constant, so it can just get soaked up in there, but it's part of the power series in order to keep that a true equal sign. There we have it. And it didn't ask for the interval of convergence, but you could try to figure out that interval of convergence if you like. It started with the geometric, but that's not what it asked for. Okay, so now I have a good idea of how to manipulate the geometric series and how to manipulate your functions to get what you're looking for. Let's do another one. Let's practice another one. So again, one more time, let's take a look at that geometric series. And you can maybe think about differentiation or integration, and there's more than one way to go about doing this, to see if you can figure out a way to find a power series representation for this function. So there is more than one way to go about this particular problem. So they're the same question as the one I just did before. Let me scroll up and give you a summary really quick. The problem that I just did before was I started with my function and I took its derivative to get it to look like my power series that I know. That's one way to do it, and it works just fine, no problem. Another way I could have done this exact same problem is start with my power series and do an antiderivative and try to get it to look like my function. It is a lot of manipulation of what you have to see if you can get what you want. So there's more than one way to go about doing that. So in this problem right here, I'll see if I can go about the same one in a slightly different way. I'm going to start with the power series and try to do either a derivative or integral of that one to get it to look like my function. Again, one more time, in the previous problem, I started with my function and did a derivative or an integral to get it to look like a power series. What I'm going to choose to do is I'm going to start with my power series and do a derivative or an integral to see if I can get it to look like a function. There's not one way that's better. There's really not. There's just other ways to solve the same type of problem. Okay, so let me start off with my power series. So my power series is, 1 on 1 minus x is equal to the sum from n equals 0 to infinity of x to the n. And this only works, of course, for the absolute value of x less than 1. This question isn't asking about the interval of convergence, but it's good to know that it's still important. Okay, so let's see what I can do. I'm going to try to manipulate this to look like that. Okay, first of all, the denominator in my function has an x squared instead of an x. So let me start with that. Let me do it one piece at a time. I'm going to start with that. That means I can rewrite that to be 1 on 1 minus x squared is equal to the sum from n equals 0 to infinity of x squared to the n. All I did from here to here is I just replaced my x's with x squared. I'm trying to manipulate this power series to get it to look like this. Okay, this power series had a 1 minus x squared in the bottom. So I'm trying to manipulate it just slowly but surely, see what I can do. This function has a squared on the outside of that entire binomial. And as we saw when we were doing the derivatives before, the only real way to do that is to take an actual derivative to see if I can get that. Let me show you what I mean by that. So now I'm going to, and I'll write this down here in a different color. Now I'm going to take the derivative, not of my function, but of my power series. There's more than one way to do this. I'm going to take the derivative of both sides and see what happens. And if I take that derivative of both sides of this equal sign, you might think of the 1 on 1 minus x squared as 1 minus x squared to the -1. And then when you take its derivative, you'll get negative. Bring the power down, subtract 1 from the power, but don't forget to multiply by the derivative of the inside because of the chain rule. So the negatives ended up canceling and I got a 2x over 1 minus x squared squared. So that was the derivative of that function. Now I need to do the derivative of the power series. So same kind of idea. Sorry for the multiple colors. There we go. Same kind of idea. I'm going to do the derivative of the power series, which you could think of as a chain rule, which you can, and it would work. But remember that x to the power of 2n is just, sorry, x to the power of 2 to the power of n is just x to the power of 2n. So then it's easier to do the derivative, the sum from n equals 0 to infinity of 2n times x to the 2n minus 1. Cool. Okay, that's pretty good. Okay, that's not so bad. It could be worse. And then one more time, remember that there's that technicality of the power series that you should not have negative exponents, but also we know that plugging in 0 is useless. So I don't need to start at 0. I can just start at 1. And then I'll go ahead and do what I did last time, which is that shift of the index or re-index it if you'd like. And now I have another equal sign, keeping track of all of your equal signs. I have the equal sign 2x divided by 1 minus x squared squared is equal to, if I reindex this, I can shift the index down by 1, but then everything else will have to go up by 1. So x to the power of 2 times n plus 1 minus 1, and I can distribute this, and that will end up with 2n plus 2 minus 1, which of course will end up as just 2n, if I can get there. There it is. Cool. All right, and then I should go back and double check, like, did I even answer the question, right? In the last strategy, I ended up having to also do an integral. Like, you don't really know. There's a million different ways to do these. This is why you got to keep track of each of your equal signs to make sure you know which is the power series, what is it equal to? Never lose the other side of that equal sign. So right now I have my equal sign that says I have a power series for this function. Cool. Is that the function I wanted? Because the last time it wasn't the function I wanted, so I should double check. So I have 2x over 1 minus x squared squared. Oh, look, it is the function I wanted. Sometimes it ends up a little easier. You never know until you try. It is the function that I wanted. So that's pretty cool. So now I know that my f of x, which the problem gave me to be 2x over 1 minus x squared squared, has a power series representation, sum from n equals 0 to infinity, 2 times n plus 1 x to the 2n. Ta-da! Awesome. I hope that helps. Thanks, guys.